Hello everyone, this is Song. Here I'm going to demonstrate the um, final research project for the class 621. Mm, it's based on the Zedboard, which consists of um, two ARM A9 core and a Arctic 7 FPGA fabric. And this research project is to implement a digital filter that can filter audio signal, music signal, filter, and after filtering it output through a DAC, so digital to analog. Here I use R2R ladder, and I have a small microphone here. Oh, sorry, small speaker. Um, I got this from a old laptop. So here, let's go through the workflow of this project. So here I use Vivado to, I will not go into deep detail, but I will just go over the project uh, quick and not into deep detail. But here is Vivado using the block design capability of Vivado to include ADC IP and as well as the Zinc processor system, and have a XE interconnect in order for the Zinc to communicate with the ADC wizard IP. And so after designing this block diagram, I generate the bit string and export it to the Vivado SDK, and I wrote some code, some software to drive the hardware that I have designed using a Vivado uh, block design. And so the ADC is sampling at uh, 6 kilo. Oh, sorry, sampling at 14 kilohertz. And what I'm having in my laptop is to play a music and to generate a tone. So we know that based on the um, sampling theorem, we can only sample signal, meaningful signal that's half the sampling frequency. So since we are sampling at 14 kilohertz, it means that we can only generate signal that is less than 7 kilohertz. And so here I have a tone generator. I went to a website that have a tone generator, and it will generate a 6.5 kilohertz tone. And so the idea is to have the music play and at the same time have this tone generator play the tone, and have the ADC pen of the Zedboard sample this signal and filter this tone out so we can hear the music only. And here I have an oscilloscope that we can use to look at the frequency spectrum of the signal, and as well as the time domain. So the yellow waveform is right now I have nothing playing yet, but it will be the time domain, and below that is the frequency spectrum. And so I also have a C# GUI application that's developed using Windows Form application. So here I will have the control of turning on or off the low pass filter, FIR low pass filter, and as well as normalizing it. So normalization will become helpful, and I will demonstrate it to you guys right now. So first, let's connect to the Zedboard. So this connection is through UART. The Zedboard have two dedicated UART hardware UART module, but I'm only using one of them right now, which is a UART 1. So connect. So now there's a Windows Form application. GUI is connected to the Zedboard, but we will have to program the FPGA. So program the FPGA. And now run the solve the code and the PS, the processing system side. So right now it's running now. Let's play the music. The music is on, and let's turn on the tone. So right now we can hear a lot of noises only, but it's due to it's not being normalized. So we'll have to click normalize. There we go. Normalization, what it's doing is that it's normalizing the filtered data such that it's within the 10-bit deck. So 10-bit meaning that I can only output values ranging from 0 to 1023. And so FIR filter, it's doing a lot of multiplication and adding, and so by the end of the processing, the output is very huge, and so we have to normalize it such that it's within the range of the 10-bit deck, so we can hear meaningful audio. So let's turn on. It's on. Let's turn it off. Let's so we can hear the difference. So that's a frequency spectrum of the signal. Let's turn it off. Sorry, turn on. So the filter is on right now. Let's turn it off. So it's very strong. The tone is very strong, very bad. So if we turn the filter on, it's a lot better. Though we can still hear the tone. It's just not as loud. If I were to pause the music, we can still hear the tone. I changed the frequency, make it higher, 6.8 kilohertz right now. But again, the filter is active. It's still on right now, and so that's why we can hear it, but just not as loud. And the frequency must be less than the tone frequency must be less than 7K. At the same time, must be bigger than 6K, because the cutoff frequency for the low pass filter is set at the knee. The knee is set at the 6 kilohertz. And so if I were to turn off the filter, that's what we will hear. Again, I mentioned that I have the frequency set to 6.8. Oh. So if we were to center this, yeah, it's here it's 6.7, 6.8, close enough. So that's the fundamental frequency of the tone. But if we were to turn on the filter, right now the tone is attenuated to a degree where we no longer can distinguish that it's a there's a tone in the frequency spectrum, other than listening to the output of the speaker, because I can still hear a little humming through this speaker. But after all, it's doing a good job of filtering that tone off. So let's play the music again. So this is with the filter on. Let's look at the frequency spectrum from the input side while the filter is on. So input side meaning that the signal is not being filtered. So let's look at the frequency spectrum. So this is the unfiltered signal, the input signal that's mixed it with music and the 6.8 kilohertz tone. So now let's look at the filtered spectrum. There we go. That's the filtered spectrum.